Good day to all of you. Today we shall study Prim's algorithm in that part 1. By the end of today's session, you will come to know what is Prim's algorithm and be able to solve a problem. That is, if a graph is given, you will be able to find minimum cost spanning tree using Prim's algorithm. Let's start the session. Prim's algorithm, it is used to find minimum cost spanning tree. Minimum cost spanning tree is a subgraph of given original graph which has collection of only those edges that connect all the vertices with minimum sum of edge weights. So minimum cost spanning tree is subgraph of given original graph. It is connected subgraph. It has all vertices but not all edges of the original graph. It doesn't have any cycles and parallel paths. It has smallest total weight of its edges. Hence it is called as minimum cost spanning tree. If the given original graph has v number of vertices, minimum cost spanning tree will have v vertices. That is all the vertices of original graph. But it will have v minus 1 edges. Prim's algorithm is greedy algorithm and has straightforward way to create minimum cost spanning tree. Greedy algorithm means a class of algorithms that make locally optimal choices at each step with the hope of finding a global optimal solution. So, Prim's algorithm finds minimum cost spanning tree. That is, it finds the subgraph of given original graph where sum of edge weights is minimum. Means it gives optimal solution. Next we shall know what are the different steps involved in Prim's algorithm. Then we shall solve a problem taking a graph. How for that graph using Prim's algorithm minimum cost spanning tree is found. Then we'll come to know how at each step Prim's algorithm applies locally optimal choices and finds the optimum solution, that is minimum cost spanning tree. Okay. Here we have the steps present in the Prim's algorithm. The step 1 is we have to start from any vertex, or in the problem whichever vertex is mentioned, from that vertex we'll have to start. We'll have to include that as the first vertex in MST. That is minimum cost spanning tree list we will have. In that we'll go on adding the vertices. So this will be the first vertex. In second step, compare the edges going out from the MST. Means whatever vertices are present in the MST list, from them which edges are going out, we'll have to compare them. Choose the edge with the lowest weight that connects a vertex among the MST vertices to a vertex outside the MST. Add that edge and vertex to MST. Keep doing step 2 and 3 until all vertices belong to the MST. So all these steps we can understand when we solve a problem. One thing to be noted here is that since starting vertex is chosen randomly, different people can choose different starting vertex. Then it is possible to have different edges included in the MST for the same graph. Means different people, depending on what vertex at the start they choose, they will get different subgraphs. But total edge weight of the MST, that is of subgraph, will still have the same minimum value. This is very important. Next we shall solve a problem on Prim's algorithm. Okay. So this is the given original graph for which we'll have to find minimum cost spanning tree. The interpretation of problem can be like this. That is, there are 6 houses. They become the vertices in the given original graph here. And these are the roads present between the different houses. And they form the edges in the graph here. These numbers written on the edges, they are the weights. Okay. So they will be representing the cost of road construction in one example. the cost of laying wires between the houses another example, or cost of networking in case of computer networking. So these are the weights which are written on the edges. Here the practical requirement is all the houses need to be connected, but by the roads in such a way that the total cost of constructing the roads is minimum. And one observation, if you see, this house, this and this, three houses, if you consider, there is a road here, another road, but there cannot be this road because it forms the cycle. So here Y cycles are eliminated here. So if this road is constructed, say cost is 8 lakhs, and next this road is constructed, cost is 9 lakhs. Already 17 lakhs will have been invested here. So then again, if you construct this road, when these three houses are already connected by these two roads, then extra expenditure of 12 lakhs is not needed. So that is what is cycles must be avoided. Okay. By keeping this view in mind, minimum cost spanning tree is framed. So this is the original graph or given graph for which we'll have to find minimum cost spanning tree using Prim's algorithm. So when we find the subgraph of this, that is minimum tree, it will have all the vertices, means it is supposed to have all the houses, but only a few roads which are required to connect all the houses in such a way that according to algorithm we'll have total edge weights minimum. So that will guarantee the cost of construction minimum. Okay. So in the process, every time instead of drawing this graph, it is transformed to this one, easiest equivalent graph. So these vertices represent these houses in the application here, and these edges represent the roads here. Okay. So in one application, this is representing construction of the roads between the houses. Or another application, if you consider, instead of roads, these may be electrical wires. So then cost of materials needed for wiring has to be reduced. That can be solved using Prim's algorithm. That is second one. In the third one, these can be the computers, and here we are doing the networking between the computers. And also here the materials for networking can be reduced, hence their cost using Prim's algorithm. This way we have many applications where Prim's algorithm is used for optimal solution, that is reducing the cost. Okay. So if there is a edge here that represents a road from a house to itself, if there is another edge that represents the second road between these two houses, so already one road is there, so this is another road. So such edges are called as parallel edges, and such edges are called as loops. There is not any necessity of constructing a road for a house to itself or constructing two roads between the houses. Hence, while solving the problem, whatever loops are there and parallel edges are there, they must be removed first. Okay. So when you transform this problem to this, the first thing is we'll have removed the loop here, we'll have removed the parallel edge here, and then continue to solve. Okay. Next, this will be our example problem. This has 6 vertices and the number of edges in the solution should be 5. So the minimum cost spanning tree, which is a subgraph of this, will have all the 6 vertices, but it will have 6 minus 1, that is 5 edges. With this, we shall start solving the example problem for minimum cost spanning tree, that is to find the subgraph of this, which gives the total edge weights minimum. Okay. So the example problem is taken here. For that we have to find minimum cost spanning tree using Prim's method with greedy approach for the graph given here, with S as the arbitrary root, means we have to start with this S vertex. Okay, let's see to the solution. Step 1, this V empty array of vertices is taken because during starting subgraph of this is empty, it doesn't have any vertex. Next, they have mentioned S to take as the starting vertex. We'll have to start with the S vertex, and that is added vertices list here, and that is chosen in the graph. Next we'll have to see outgoing edges from S. So from outgoing edges from S are this edge with weight 8 and this with 12, that is what is mentioned here. Now at this step choose the optimal, means 8 is the minimum and hence minimum which is 8, that is chosen, and for that which vertex is connected, that vertex is chosen, that is B vertex. So out of weights 8 and 12, 8 is found to be the minimum which is connected to B vertex. So instead of A vertex, after S vertex, B vertex is chosen. So B vertex is added to the list and the edge between S and B is connected. So till this step, this is our minimum cost spanning tree. This is our subgraph representing minimum cost spanning tree. Here it is mentioned in the form of list of vertices here in the graphical representation. So at present till this step, in minimum cost spanning tree vertices list we have S and B, and in the graph it is shown S and B vertices are present and they are connected with this edge. Okay. So next we'll have to observe this MST list, minimum cost spanning tree list. We have two vertices here, S and B. For that we'll have to check in the graph S and B, do they have any outgoing edges, first point, and if they are there, among that we'll have to choose the edge with minimum weight. That is the next step. If you observe S here, it has two outgoing edges. This is already covered, so edge with 12 is taken and that is what is written here. B vertex has 1, 2, 3, 4 outgoing edges. This has already been covered and hence the other 3 edges, one with weight 9, another with 14 and 16, they are chosen and they are written here. The minimum among these is 9, that is taken. So we have to choose the vertex A. So A is added to the MST list here. It is marked in the graph. Then B and A vertices are connected. So till this step our minimum cost spanning tree is this list, which has S vertex, B vertex and A vertex. And in the graph it is shown here S vertex and B vertex and A vertex, and they are connected through these two edges. So this is the status till this step. So if you take A, so from A, outgoing edges, this one with 12, second edge with 9, this with 11 and this edge with 22. 4 edges are there. One edge is already covered, we shall not consider this. If you take this edge, it forms the cycle, will not consider this. Then remaining only 2, the edge with weight 11 and 22 will have to consider for A. That is what is written here. For B vertex, if you observe, so B vertex is here. There are 4 outgoing edges. 2 are already covered. The remaining 2, the one is with weight 14, another with weight 16, and that is what is mentioned here. So if you see to S vertex, so S vertex is here. It has 2 outgoing edges. This already covered. If you see to this, it forms the cycle it cannot be considered, and hence here onwards we will not write about S, and this is not mentioned here also. Now among these we'll have to choose minimum weight. The minimum is 11. So that edge is present here, which will be connecting A and E edge. So minimum is 11 and we have to choose the vertex E. When vertex E is chosen, that is added to minimum spanning tree vertices list. And in the graph, vertex A and vertex E are connected. Till this step, the status is the minimum cost spanning tree has 4 vertices S, B, A and E. In the graph they are shown S, B, A and E. So S to B is connected, B to A is connected, A to E is connected. So S to B is connected, B to A is connected, A to E is connected. So this is the status of minimum cost spanning tree subgraph till now. In the next step, we'll have to check for these vertices in the graph if they have any outgoing edges, and then find the minimum among them. And that is what is written here. If you take edge E here, so E in the graph has got 4 outgoing edges. This one is already covered. Then we have 3 outgoing edges, one with weight 3, another with 14, and the third one with 18. That is what is written in the list here. Similarly for vertex A, so vertex A is here. There are 4 outgoing edges. These 2 are covered. This we will not consider because it forms cycle. We have only one edge with 22 weight, that is what is mentioned here. For vertex B, so vertex B here, there are 4 outgoing edges. 2 are already covered. We have only 2 edges, one with 14 and another with 16 weight. That is what is mentioned here. Here for vertex S, so vertex S is here. There are 2 outgoing edges. This is already covered. So we have only one edge, that is with 12, but it is forming cycle as already mentioned, that will not be considered. So we have for B, A, E, the minimum among this is 3. Hence we have to choose vertex D. Because edge with 3 weight is present here, it is connecting E and D. So D is marked here. D is added in the MST vertices list. E and D edges are connected. And this is the status till this step. In MST vertices list we have S to B, B to A to E and D. So that is what is shown in the MST graph here. S to B, B to A to E and E to D. We shall see to next step. In the next step, for all the vertices in the MST vertices list, we'll have to check for any outgoing edges are there in the graph and choose that edge with the minimum weight. Okay. All those details are mentioned here. If you take D vertex, so D vertex is here. There are 2 outgoing edges. This is already covered. We have only one edge, that is with 15. That is what is mentioned here. If you take edge E, which is here, it has 4 outgoing edges. 2 are already covered. Then we have only 2 edges, one with 14 and another with weight 18. That is what is mentioned here. Next, if you consider vertex A, so which is here, it has 4 outgoing edges. This will not consider, it forms the cycle. These 2 are covered. We have only one edge with weight 22. That is what is mentioned here. If you take B vertex, which is here, it has got 4 outgoing edges. 2 are already covered. Then we have edge with 14 and another with 16. Those 2 edges are mentioned here. So yes, will not consider because one is already covered, the other forms cycle that we have already mentioned. So yes, we will not consider. Out of this, minimum is 14, but that we will not take. It forms the cycle here. So the next minimum is 15. So that is considered. So the edge with weight 15 is present here that connects D vertex with C. So we'll have to choose the vertex C. When vertex C is chosen, that is marked in the graph here, and that is added to MST vertices list. C and D vertices are connected. This is the status till here. MST list of vertices has S to B, B to A to E, E to D, D to C, which is shown in the subgraph here. To B, B to A to E, E to D, D to C. In next step, if you observe, the subgraph has all the 6 vertices. So in the subgraph, all the 6 vertices we have got. Okay. So 6 vertices were there in the original graph. Now in the subgraph we have all the 6 vertices. And the edges present are 6 minus 1, 5. 1, 2, 3, 4, 5. So the procedure is completed. So MST vertices list is completed. So this is our final solution. Minimum cost spanning tree, which is expressed in terms of list of vertices. And this is the minimum cost spanning tree, which is the subgraph of original graph, which has same number of vertices as the original graph. But according to Prim's algorithm, what edges are chosen, which can connect all the vertices, still maintain the minimum cost. And that is what is minimum cost spanning tree, which is found from Prim's algorithm. The minimum cost is sum of all these weights, that is 8 plus 9, 9 plus 11, 11 plus 3, 3 plus 15. That comes out to be 46. That completes the solution. So for this original graph, we had started from here and we have arrived at the solution for minimum cost spanning tree using Prim's algorithm. So this is the minimum cost spanning tree subgraph, and this is the list of vertices which expresses the minimum cost spanning tree in the form of vertices list. And the minimum cost is 46. In the next video sessions, I will be solving some more problems on Prim's algorithm. I hope you have understood. Thank you.